Hello astronomers, this week we're going to be talking about stellar evolution, and in particular the stellar evolution of low-mass stars. So in your readings this week, I've given you a link to NASA's stellar evolution flowchart, and this gives us kind of a handy way of looking at how stars form and evolve, and what determines what type of stars they become in the end. So I just wanted to run through that really quickly so you could see what that looks like. First of all, stellar evolution begins with collapsing clouds of dust and gas, and by gravity alone these things pull together until they get hot enough that the interiors ignite into stars. And stars, by definition, something that's producing its own energy through fusion inside the star. This process happens relatively quickly, a few million years, and that leads to the nebula that produces the star. That star-producing nebula is called a protostar, and the type of star you become depends solely on the mass of this protostar. So if you happen to be a mass much smaller than the sun, you're going to turn into a brown dwarf or a red dwarf. If you have the mass the same size as the sun, you'll turn into a sun-like star, and if you have a much more mass than the sun, you're going to turn into a blue supergiant, a very bright, short-lived star. The main defining feature of all of these stars is that the bigger they are, the hotter they burn, and because they're burning so hot, they don't live as long. Even though they happen to have a lot of fuel for nuclear fusion, because their luminosities are so bright, they don't burn for very long. So this week we're going to be focusing on what happens to sun-like stars, and that's the left-hand side of this flowchart. Sun-like stars, we have nuclear fusion, which is going to consume the hydrogen and turn it into helium, and there's some nuances in there about what type of process is used, but you'll be learning about that in your chapters. But you're taking hydrogen gas and fusing it into helium, and there's a slight mass difference between those things. That mass is converted to energy and it comes out as radiation. Now, because the gravitational collapse of the star is exactly balancing the radiation pushing it out, the star remains roughly the same size for its lifetime until it's done burning its hydrogen fuel. Once it's burned through its hydrogen fuel, it begins to collapse, and as it collapses, it starts to fuse helium into heavier elements, and when that collapse occurs, the core heats up. That creates a little bit more radiation pressure, which pushes the envelope of the atmosphere of the star away. And as the material is ejected, it forms something called a planetary nebula. These are things we can see through our telescopes. And inside, that central star is going to collapse into something called a white dwarf. That white dwarf is effectively going to sit there for the rest of the universe, slowly cooling off. Nothing much else is going to happen. If it does happen to have some extra mass added to it, say for example from a companion star that happens to be orbiting it, and it gets over about 1.5 times the mass of the sun, it can explode into something known as a type 1a supernova, and you're going to be learning about those in your chapter this week. So that is the evolution of low-mass stars. That's something that's going to happen to our sun, and when the part of this evolution is when the star begins to the core begins to collapse, the star begins to expand into something called a red giant, and that red giant can be enormous. It's going to engulf the planet Earth, but don't worry, that's only not going to happen for about 5 billion years. So that's stellar evolution of a low-mass star, and you're going to be looking at how that works this week. Talk to you later.